Good afternoon, guys. We are still plugging right along in Unit 2. Some of you are getting your quizzes turned in. um, I'm not going to post this video until Wednesday, but right now, currently, it is Tuesday. So several of you have gotten your quiz in to me. I'm still hoping to hear from several of you that I've not heard from since we've gotten out of school. You guys know if you've spoken to me. If you have not, then you really need to do that so that I know you are still with us and participating, because I cannot stress enough, especially for you all and the stats class, how important it is that we continue to move forward, because this is a college level course, and you are going to get college credit for it, or you are not going to get college credit for it, but it will show up on a college transcript. So, you need to take it serious if you've kind of been brushing it off, and start getting a little bit more engaged with the class. Right now, we are looking at complex zeros of a quadratic. We have talked about the real number system pretty much exclusively in this class. And when we talk about the zeros of a quadratic, remember that is where the graph crosses the x-axis. A quadratic function will have 0 real zeros, which means it never crosses the x-axis. It'll have 1 real zero, which means that the vertex touches the x-axis. Or it can have 2, which means both arms of the quadratic graph itself cross through the x-axis. And we'll look at these first two examples here and kind of discuss that a little bit. It does say to find the complex zeros of each quadratic. In the case of part A, there are no complex zeros in the sense that there is an imaginary root involved. One thing that I want to mention that is not included in these notes, we're going to talk about later on, we're going to go into more detail with complex zeros, is a complex number can be expressed in the form a plus bi, where the a is the real part of the number and then the bi is the imaginary part. And a and b can be any real numbers. So if let's just say, I'm trying to think how to explain this. Up to this point, everything you've ever dealt with has been in the real number system, and up to this point, you've been led to believe that the real number system is it. That's all the numbers that exist. However, the real number system itself is a subset of the complex numbers. The complex numbers do in fact end up encompassing all of the numbers that we know that exist. And I'll give you an example here, and then we'll go on and work through parts A and B here. But the number 5, for instance, is a complex number because we can express 5 as 5 plus 0i. So it's 0 times the imaginary root, which is still 0, and we just get 5. So every real number can be expressed as a complex number, which leads us to the conclusion that the real number system is a subset of the complex number system. Anyway, we are going to, like I said, talk about that a lot more in detail later on in a different set of notes. But for now, we're just looking at how to find these complex zeros. And with part A, we have this quadratic x squared minus 4. And if we're looking for the zeros, then we must set the quadratic equal to 0. This one looks to be easily solved using the square root method, so we'll add 4 to both sides. And then take the square root of both sides. And the square root of 4 ends up being 2. So we get x is equal to plus or minus 2. If I wanted to express this as a complex number, it would be plus or minus 2 plus 0i. So positive 2, negative 2 are the solutions. Now for part B, we do encounter something a little bit different. If we start out with the same steps, we set the quadratic equal to 0. We subtract the 9 from both sides. And then we use the square root method. Well, this is where we encounter the one of the rules that you have been told many times over. You cannot take the square root of a negative number. What I'd like to do is take that negative 9 and I'd like to break this down a little bit further. one nice thing about square roots is we can separate multiplication. So I think we can all agree that the square root of 9 times the square root of negative 1 is still exactly the same as the square root of negative 9. What we do know is that the square root of 9 is 3. One thing that we have not talked about yet is the square root of negative 1 is what we call the imaginary root I. So a little side note here, square root of negative 1 is equal to I. And anytime we have I squared, that's equal to negative 1. Again, that's going to come up much later in a different section, but we will be discussing this quite a bit more later on. But right now we're just looking at how to find the complex zeros of quadratics. I will illustrate to you graphically what we're looking at here. So let's consider example A, which was x squared minus 4. You can see we have these two distinct points where the graph crosses the x-axis. Those are its zeros. But now what about in the case of x squared plus 9? When I graph that, I need to zoom out a little bit here. You can see that the graph of x squared plus 9, which is this red graph that shows up on the screen, it lies completely above the x-axis. It has no real zeros because it never crosses the x-axis. However, it does have roots in the complex plane, which we just found to be positive and minus, or positive and negative 3i. The alternative would be a graph that lies completely below the x-axis. That also has no real roots. They're all complex. But real roots only exist when a graph crosses the x-axis. When we move on to example 2, again it says to find the complex zeros of each of the following quadratic functions. The first one that we have, part A, it's x squared plus 6x plus 2. So ask yourself, do you know of any values that are factors of 2 that when we add them together we get positive 6? Nothing comes to mind to me right off the bat, so I would be inclined to use the quadratic formula first. And the quadratic formula, just to refresh your memory, is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So when we substitute in our values for a, b, and c, what we end up with is x equals opposite of b plus or minus b squared minus 4 times a times c all over 2 times a. And we end up with negative 6. We're going to have 36 minus 8 over 2. And then you get negative 6 plus or minus the square root of 28 over 2. We can simplify that a little bit further. Let's see, that would be negative 6 plus or minus 2 radical 7 over 2, which simplifies to negative 3 plus or minus radical 7. Okay, so this one does have real zeros. They're not necessarily complex because this graph would cross the x-axis at negative 3 plus radical 7 and negative 3 minus radical 7. For part B, we're going to do a similar process. We're going to use the quadratic formula, and again we're going to have the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So here we get 4 plus or minus 16 minus 32 over 2. And here the discriminant, the value that's underneath the radical, is negative. So that indicates to us that we do have two complex zeros to this quadratic. And similarly, what we did in example 1, we can rewrite the square root of 16 as 4 plus or minus the square root of 16 times the square root of negative 1. I'm not saying that you have to write that step out every time. If you're comfortable enough going ahead and taking the square root of 16 and throwing an I on the end of it, that's fine too. So we end up with 4 plus or minus 4i over 2, which does reduce to 2 plus or minus 2i. So the zeros for part B are going to be 2 plus or minus 2i. So that means that this graph lies either entirely above, or actually this one would, because the quadratic term is positive, this graph lies entirely above the x-axis. So it never crosses the x-axis. So we would have to have these two complex zeros. The discriminant of any quadratic tells you about the character of the solutions. And we've talked about this in previous notes as well. If the discriminant is greater than 0, meaning that it is positive, then we have two distinct real solutions. If the discriminant is 0, then we have one repeated real solution, and if the discriminant is less than 0, or if it's negative, then this discriminant, or this quadratic, would have two complex solutions. And for example 3, which is the last example in this set of notes, we're just going to determine the characters of the solutions for each one of these problems. So we're only interested in the discriminant, which is the square root of b squared. We don't have to have the square root, sorry. It's just b squared minus 4ac. And we just want to evaluate that and determine, is it positive, 0, or is it negative? So for part A, we would have 4 squared minus 4 times 3 times 5, which gives us 16 minus 60, which would be negative 44. Okay, all we're interested in is whether that's positive, 0, or negative. In this case, it's negative. So this would mean we have two complex zeros. That's all it's asking for, is the character solutions. For part B, again, it's b minus 4ac. So we have 4 squared minus 4 times 2 times 1. We get 16 minus 8, which is 8. This is positive, so this means we have two real solutions. And then finally for part C, we're going to do the exact same process. B squared minus 4 times A times C. We get 36 minus 36, which is equal to 0. So we have one repeated real solution. Okay, and so that is the complex zeros of a quadratic. We're not going to focus too much on the definition of I as of right now. That is going to come up later. Right now we're just more interested in being sure that we can find these values. So anytime you have the square root of a negative number, that's when you know you have a complex root. So I hope that these do not prove to be too challenging for you. If you have problems, there's only 10 of them on here. So maybe you get motivated on these NTI days to just do all 10 problems. I hope you guys are doing great, and I will be talking to you soon.